Well, hello everybody and welcome back. So here's our next project. It is a Kenwood model KR750. And the whole 700 series Kenwood receivers are kind of unique. I actually got a KR710, which was the little baby. That was the entry-level model, the year that they came out. And it was 28 watts per channel, and it had manual tuning, but it actually performed really well for a little 28 watt receiver. This one is a couple models higher. They have the 720 and the 730, and I don't remember if there was a 740, but each one was a little bit more features and a little more power. This one's 60 watts per channel, and it has some pretty amazing specs as far as distortion and so forth is concerned. But really the unique thing about this is the weird tuner that's on it. There is no manual tuning. It's only auto tuning, and it has a frequency counter here, so it has a digital display for the tuner, but also has an analog display, if you notice. And when you tune, I mean, you can hear it, and you could see. And to tune, you just hit the button, and you could see it kind of locks in on the station. The only way to get it to manually go somewhere is if you turn on this preset button, and then you can move these little sliders, and wherever there's a slider, the tuner will go to the next slider. And you can see it'll stop there. And you can see this green light is flashing because it's unable to lock on a station because I did not put it over a station. Now if I take this and I actually put it over top of a station or close to, and you can see and you could see, and it's still not totally locked on the channel. But if we turn this off, there, and you can see it'll lock in. So it's kind of an interesting tuner. It kind of drives me crazy because I'm one of those guys that likes to tune around and find the weak stations and so forth. Ain't gonna happen with this tuner. Oh, it's just kind of one of those things. It's a gimmick, and it was designed for marketing and for sales. But if you can look past all that, these actually have pretty nice amplifiers in them. And for the time in which they were built, which was the late 80s, maybe up into the early 90s, these were pretty good little receivers for the price. They were a bargain at what they were selling them for compared to some of the other gear out there. So let's take a look inside. Okay, we're in. So one thing right off the bat I noticed taking the screws out, I could feel the heat of this heatsink. It is getting really, really warm. It's not burning your hand hot yet, but it's really warm for just sitting idle. This other little heatsink, which is actually pretty tall under here, you can't really see it very well. You can see right inside here. That sucker will burn your finger if you even touch it. So some of this stuff's running pretty warm. The other thing I noticed is the power meters. The right channel seems to be a little bit weaker than the left. And if you pan over to the right channel, there's very little treble. It's really muffled sounding. So that could be a bad capacitor, even though I wouldn't expect that on this vintage of a machine. Very unique tuner, and even though it's all automatic and it has a frequency counter, for digital display, this is not a digital synthesized tuner. It has a normal tuning gang, and I don't really see that it has a PLL circuit in it. I haven't looked into it or read the theory of operation yet, but it looks like kind of like just a fancy traditional tuner with a little motor on it. So that it can do that auto tuning thing and some extra circuitry to allow that. But other than the auto tuning, it is a very common basic tuner. So well, the real thing we got to look at, the tuner's working fine. We have to figure out why this amp has a problem on one channel and why the heat sinks are getting so warm, and it's getting warmer and warmer here. So I'm going to shut it off. So that's our thing for this video, I guess. Figure out what's wrong with the amp. Okay, I'm looking at the output of the speaker terminals and can see why those things are heating up so much. This one's not too terrible. It's not good, but this one's way off. And it's probably because these little potentiometers here are dirty. So let me adjust this. There we go. Yeah, this pot's real dirty. It's jumping all over the place. So let's clean it and see if we can get it to adjust better. Okay, there's the pots we want to clean. And I just took a little bit of deoxit and just sprayed it in the bottom of this container. And I have one of these little makeup swabs that's used for applying like makeup, I guess. You can get them real cheap online. And you just dip it in there. And I have the amp turned off. And we're just going to kind of go in there and just clean around it a little bit. And it'll actually wick up inside there. You don't really have to rub it on there too hard. It only takes a tiny little bit just to, and it'll like I said, it'll wick down in there. The actual fiber on that will actually soak it up. And that's really all you need to do, just a little bit on each one, and that'll do it. And then just work them back and forth. And of course it's going to be off by a country mile, but that's okay. Oh yeah, look how easy those are to turn now. They move real easily now. Alright, and we'll do this one. Just like that. And now let's see if we can get them to adjust now. Okay, they're both way off, so let's adjust them. We'll do the top one first. Just kind of let it stabilize a little bit. And then go to the bottom one. Oh wow, much better. There we go. And they're both very, very low offset now. That definitely will help. Yeah, just kind of have to play with it a little bit to get it right. There we go. And just so it's within a couple of millivolts, it's no big deal. Plus or minus, 20 millivolts, 10, something like that. It'll be just fine. So there you are. Now let's check our bias and see if somebody cranked that up, or if it's just the same thing, has a dirty potentiometer. Alright, to set the bias on these, even though I thought these were all connected, they are not. These are 4 separate heat sinks, and you can see these little stabilizer bars in between. They're insulated, but this and this are 2 separate heat sinks. And in order to measure your bias, they want you to measure between the 2 heat sinks, which are electrically connected to the center pin of the transistors, and they want you to have 44 millivolts. So basically all you have to do is put your probes right in those little screw heads, and you can directly measure the bias there and here. Now not here, because this is the 2 channels, but these 2 screws and these 2 screws down here will give you the bias for right and left channel. So let's move up to our meter and see what we got. And it's supposed to be 44 millivolts. And that's not bad at all. It's 46 before we even touch it. 47. So if this pot's dirty, it'll jump all over the place on us. Nope, this one's running pretty good. So you want about 44 they're looking for. And you just kind of have to move it a little bit and then let it settle. That's pretty good there. That's about as good as you're going to get it. Let's go to the other channel. And okay, and it's a little bit high. I think that DC offset was our biggest problem. So let's turn this one down. That's pretty close right there. Won't hurt it. Within a couple of 1 millivolts, not going to make that big a difference. Okay, so we'll just let it cook for a little bit and make sure it doesn't drift a whole lot. And if everything's good, then the amplifier is set. And if it still runs warm, I think it's just going to be because of the undersized heat sinks. And you know, looking at it now, first of all, you don't have the thermal stability between, you know, the transistors because they're on not on a common heat sink. And second of all, you look at these little tiny heat sinks, how tiny they are. You know, it's just there's one, there's one, there's one, and there's one. They're so small. They're really undersized for those big transistors. If you look, they're those MT200 style transistors, which is similar to those big oval TO3 ones we see. That's a lot of power for a 60 watt per channel amplifier. So really, I would have liked to have seen some larger heat sinks on this. And you can see where Kenwood, you know, in this mid 1980s, early 1990s era, where they started cutting corners on things like that. Good amplifier, just cutting corners on the heat sinks. The main filter caps are a little bit small. You know, all this stuff is just, you know, the bare minimum. And they run pretty warm. So these transistors can take it, but I just kind of like to see it a little bit better heat sink than that. All right, we're connected up to our 8 ohm dummy load. And you can see right here is going to read the output for channel 1 and channel 2. And the red line is your FFT. And you'll see the 1 kilohertz tone come up. And as soon as we see the harmonics start to rise, we know we're at distortion, even though you can kind of see it in the sine waves too. It really doesn't matter. But we're going to measure our output. And the most important thing is I want to see if these numbers are pretty accurate. And I can tell you this amp does run hot. It really does. These little heat sinks are not enough for this amplifier. So let's turn it up. And just so you know, around 23 volts, which this is on times 10 right now, so 23 volts, which would be 2.3 volts here, would equal right around 65 watts or so, 66 watts, something like that. So here's our 1 kilohertz. And we're going to come up till we start to see some distortion. And you can see, if you go up too far, you see these peaks. And we drop it down, they drop right down. So right about there. And you can see we have about 23 here and about 24 here, roughly. So it's about 1 volt different, that's pretty respectable for these amps. I mean, when you have analog potentiometers for the volume and balance, they're not always totally perfect. And you'll see that. That's why the more expensive preamps and so forth out there will have those stepped attenuators. A stepped attenuator is actually, instead of a potentiometer, it's a switch with a whole bunch of taps on it. And each tap has a different resistance, and you bring in those different resistors for the different volume levels. And it's very accurate because they use highly precision resistors for both channels, so that when you rotate the volume knob up, that stepped attenuator, you are actually inserting known accurate values of resistance so that both channels are going up equally. With the pot, you have a wiper going across a piece of carbon, and there's always a chance for there to be a little bit of difference between the two. So you see that. You won't hear it so much in your ears, but you can see it when you measure it like this on a scope. So you can see as they come up, the voltages are a little different. And sometimes they'll be closer to one another, and sometimes they'll be further apart, depending on where the volume knob is. And that's just the difference in the carbon tracks on the pot. So here we are. So not bad, but I can tell you, going down here, these heat sinks are, I can't keep my hand on them. They're too warm. And let's just, for giggles and grins, let's just see. Come on and focus. We're getting 57 degrees Celsius, which is the same as about 140 degrees Fahrenheit. So yeah, those are getting very warm. I wouldn't expect that little tiny test to heat these up that much, but it does. And they're all four equally, I mean, they're all pretty much the same temperature. So kind of gives you an idea the undersized heatsink problem on this. So that's one thing I would say about this receiver that I'm not crazy about. And I'm also not crazy about only having automatic tuning and not having a manual tuning in there as well. But there it is. That's it. Okay, let's do a little test on the sensitivity of this tuner, because again, the ability to tune in weak stations, it kind of scares me on these auto tune things. So I have a right now I just have a carrier signal only, and I'm putting out about 10 microvolts, and we're just going to see, and which is a fairly strong signal. I mean, it's a weak signal, but it would have static in it, but it should pick it up. And I have it attached to my little impedance matcher, and I'm tuned right to the center of the band, which is 98.1 megahertz. You can see 10 microvolts, and let's just see if this thing can pick it up. And again, there's no modulation, so there won't be anything but a little bit of hiss in the background. So should stop. Okay, that's noise. You can hear noise. And there we go, 98.1. And you can see when I turn it all the way up, you hear that little bit of hiss. I don't know if the mic's picking it up. So now let's see how far down we can go and still stay locked on to the station. So let's go down to 5 microvolts. And you can see we lose it. Let's go up to 6 microvolts. And it comes back. So you can see at about 6 microvolts, that's about as small of a signal as this tuner can actually tune in, which is not very good. Most receivers can tune a station in down to about 2.5, somewhere around 2.5 microvolts. With this particular setup on my bench the way I have it. So, and if you recall on the STA 2200, it was picking up at 2 microvolts with no problem whatsoever. Now that's not because this is a analog tuner, because like I said, an analog tuner can do this, can be just as sensitive as a synthesized tuner. It's just that either A, this is not a very good tuner at all, or B, what I'm suspecting is that maybe it's a little bit out of alignment. I don't know if I'm going to go through the alignment on this or not. I might. But there it is. I mean, that's how you test it, though. And if I turn on the modulation at 6 microvolts, we should be able to hear something. Oh yeah. Nice and loud. Now, sometimes when you put modulation to it, you can get the signal down even further. So let's see if we can do that. So now we'll go down to 5. Wait a second. 5 microvolts. And you can see it still loses it. And you can hear it just barely in the background, but it's actually muting it out. And the reason it's muting it out is because it doesn't think there's a channel there. So it's open. If I go back up to 6 microvolts, it comes back on. And you can hear it. So there you go. That means this tuner's either out of alignment or not very sensitive. So there you go. Alright, you know I can't leave well enough alone. That just ain't me. So we're looking at the discriminator right now, and it's just these two test points. And just like every other tuner, the discriminator, when there's no signal, that means there's no deviation. In other words, you're right on frequency and you're not drifting above or below frequency. You're not modulating that frequency. So in theory, it should be centered, meaning there's 0 volts on it. And then when you have your audio signal swinging up and down, above and below frequency, you should see that frequency, that voltage, go one direction or the other, or both. If it's shifted to one side, that means the discriminator is not centered, and what's going to happen is, number one, it'll weaken your signal a little bit, but number two, as the amplitude of that signal gets bigger, you get a louder signal, it'll start to clip on one end and you'll get distortion. So in order to fix that, you have to null out your discriminator. It has to be at 0 volts. So I connected up a meter, and we can see right up here, we're on a point of there's no station. It's quiet. I turned the volume all the way up, just barely any static at all. I have the RF turned off on my signal generator and everything, and you can see there is 200 millivolts sitting on that discriminator. So what that means is that we actually do have some noise on there, and we're going to have to adjust it. So let's turn the little discriminator coil and see if we can get it to come in. Okay, here we go. Here goes nothing. How about that? Wrong way. Went over it. It's a very, very touchy adjustment on this thing. And this has to be at 0 volts if possible. The closer to 0 you get it, the better. And you can see if you just barely move it too much, it'll go over. That's pretty good right there. I mean, we're looking at, millivolts right here. And that's tenths of a millivolt and hundredths of a millivolt. So we're pretty close to 0 volts. A lot better from 200 millivolts. Okay, the next one is our auto frequency control, AFC. And if it's tracking properly with no signal, it should be applying no correction, and it should be 0 volts once again. And you can see, again, it's upwards in that 100 to 200 millivolts. It's jumping around a little bit, but definitely needs adjusted. So let's do our AFC adjust, and we'll rotate the little adjustment for that and see if we can get it a little bit better. And again, very jumpy. It's a lot easier with an analog meter if you have a vacuum tube voltmeter, which I do have several of them, but I'm just too lazy to to get them out and set them up. But you can see it's passing through between negative and positive, so it's actually sitting at 0 right now, and you're just seeing kind of noise on the meter. So that was out a little bit as well. Every little bit counts. Okay, for our next test, you guessed it, it's the second discriminator adjustment, and this is where we adjust for minimum distortion. And you guys ought to be old pros at this by now, huh? As many videos as we've done this. So here's our output of our recording jack on our out of the tape out jack, and you can see we have our 1 kilohertz modulated signal. And the instructions for this tuner is asking for 60 dB. Now, that's not dBm. It's not what you think. That's a lot of the Japanese receivers will use dB instead of microvolts. Those are two different ways of saying the same thing. And there's actually little charts you can get to convert it. But 60 dB is the same as 500 microvolts. Long story short, they're looking for a strong signal. If you recall on the STA 2200, they wanted 1,000, or they wanted 1 millivolt, which was 1,000 microvolts. This one, they want you to do the adjustment at 500 microvolts. It's still a very strong signal considering that this is supposed to be sensitive down to 2 or 3 microvolts. So what to take away from this? Put put a strong signal middle of the band, 98 megahertz. They want 98 on this machine instead of 98.1. And we're tuned to that right now. And we're going to adjust this little guy right here till we get our minimum distortion on our distortion meter. So let's get you connected so you're not dizzy anymore. And I have a new camera mount coming because this one's starting to annoy me. And let's adjust it. That's the wrong way. Wow, look at that. What do you think? Okay, so we've made some pretty good adjustments on this. Maybe this thing will be a little more powerful than we think. Maybe we can get that 3 microvolts that we wanted. Okay, we have it all back together. Let's see if our little adjustments made any difference on anything. I have, we're dialed into 98.1 megahertz, and that little, the small digit there actually is the 0.5 or 0.05 megahertz. So actually, if it's off a little bit, there's a frequency counter. This is actually a frequency counter. In other words, this analog dial is connected directly to the tuning gang, and this is nothing but a frequency counter. And just like any other frequency counter, you can adjust it. There's a pot inside there. And basically, once the dial alignment is correct on the analog dial, all you do is you adjust the frequency counter to match up with that. So it's one pot, very simple. So we have it all lined up, and we have our 6 microvolt signal. You can see right up here. And of course, just like before, it works just fine. So now let's drop it down and let's turn the scope on here so we can actually see, so I don't have to keep playing that horrible tone in the background. Hold on a second. Okay, so we can hear our tone, and we can see our tone now, so I don't have to play it. So let's drop our signal down to 5 microvolts. If you recall, before we tried this, and there we go, 5 microvolts. And you can, and it's still picking up, and it's still locked. So let's go down to 4 microvolts. And you're starting to see a little bit of static. And you can hear a little bit of static. But it's still picking up 4 microvolts. Let's go down to 3 microvolts and see if it stays locked. And we lost our lock, and it went out at 3 microvolts. Let's see if it'll do 3.5. Yep, 3.5 microvolts. So it's not the most sensitive receiver in the world, but it's acceptable, it's average, and pretty interesting. Now again, like I said, and this little 0.05 will toggle back and forth. It's almost impossible to get it right on. It just, it's kind of sensitive. But we can see even at 3.5 microvolts, it's kind of the cutoff point. And so the receiver is somewhat sensitive, but not nearly as good as some of the others. So some things to take away from this little video, and that is, number one, the tuner's not super sensitive, and it is not a digital tuner as per se. It's an analog tuner that has a scanning circuit that kind of looks for the peaks wherever there's a station. So it'll see a peak in amplitude at a certain frequency, and it'll kind of try to lock onto it with that little motor drive assembly. It's kind of a unique little design how they did it. Interesting. The amplifier, even though it's a pretty good amplifier on paper, and it sounds good, I will admit it sounds really good, definitely under-engineered with the heat sinks. They're way too small for those big transistors, and as a result, even on idle, they run very warm. And if you try to push any kind of difficult load or any kind of high volume through it, expect the amp to run really hot, which is never good. So really, if you wanted to purchase one of these on the used market, they're great little performing receivers, but there's a lot of plastic parts and a lot of things that run really warm. So I would highly recommend, and that tuning circuit is probably susceptible to failure. So really, you want to make sure it's well tested and that you know that it's a reputable seller when you buy one of these, if you're going to buy it used, or you're going to need the wherewithal to repair it. There's a lot of these on the market, and they can be picked up very inexpensively. And they actually, like I said, they sound pretty good, but just be aware of those things. My KR710 that I had was a totally analog tuner. It didn't have finned heat sinks. It just had like an aluminum plate for the transistors, but being only 28 watts per channel, it ran a lot cooler, and it was a very reliable little receiver. And to be honest, even though this has double the power, sound-wise, they both sounded very similar, other than this one will go a little bit louder. And the tuner, I would say, if I recall, I gave it to a friend in college many years ago in the 1980s. And I'm sure they're probably still using it, who knows. But again, good little receivers. Just make sure you know what you're getting into if you're going to buy one of these higher end models like the 730, 720s. Those, they all had this kind of tuner, starting I think with the KR720, if I'm not mistaken. But that's enough on this video. A ton of more things to do on the bench here, so I need to get this off the bench. I hope you enjoyed it. I know I didn't cover a whole lot of things, but I really didn't have the time on this one and just wanted to get it done. So you all have a great day, and peace, joy, happiness, and good health in all your lives. I wish you all well, and we will see you next time around. Take care. Bye-bye.